I don't know. Okay, well, today we will talk regarding the image resortation, and as the lecture 11 that we have, some agenda we have regarding what is image resortation, model of the degradation and resortation process, as well as some algebraic approach to the image resortation. First of all, we should talk regarding the image resortation. This image resortation is the way to reconstruct or recover an image that has been degraded using some prior knowledge of the degradation phenomenon. Image resortation usually involves formulating presentation of goodness that will yield an optimal estimate of the desired result. Thus, this is something like objective process. Maybe you will ask me then, what about image enhancement? You know, enhancement technology basically are some heuristic procedure which designed to manipulate an image in order to take the advantage of the physical aspect of human visual system. Thus, again, this is something like subjective process. Then see, the difference between these two concepts is something like this, that the image resortation is objective and enhancement is some subjective. If you want to make it more clear, I can say that image resortation attempt to restore the image that have been degraded and identify the degradation process and attempt to reverse it. And similar to image enhancement, but more objective than image enhancement. See the figure, suppose on the left side hand, you can see the original image before the resortation, and at the right side, this is the picture after resortation. Again, if we want to make this border clear, we can say that image enhancement is largely a subjective process, that enhancement techniques basically are heuristic process and designed to manipulate an image in order to take advantage of psychological aspect of human resource. And again, as I say, image resortation is an objective process. But this degradation process, if we want to make the modeling from that, we can assume such these blocks. You'll see that here you have some degradation phase, and after that you have some restoration process, which in that initially, if again you think the figure and picture that we have in the form of f, x, and y, then it can enter to our degradation function, which we call it h. And then after that, with the parameter of eta, which will be act on each x and y, we can have the function of j, x, and y as the output. And then with the help of some resortation filter, we can have the f bar x and y. This is the degradation function with some additive noise term. Means that eta is some noise which will be added to that, and then we can remove it or have the better feature. Degradation process modeling, as we show here, it's as the function, it is with an additive noise term, which we call it, and we can use the H as a linear and position invariant process. And degraded image is given in the spatial domain by the formula that we show here. This star that we have, we call it convolution, which we will talk more in the image processing part. And here now you can see the G, X, and Y, and you will see the H, X, and Y as the linear position invariant process, and the function which act on the F, X, and Y, and eta, which will be add to that. This is nothing but the block that I showed in the previous slide. And the equivalent frequency domain representation is something like this, as we saw. And we can have the model of the restoration process, which is combined with the degradation. You will see here the image degradation process is can be modeled as the system H together with the additive noise will come with the term of the eta x and y here as the summation that you can see, and will act as the input image. Then f, x, and y to produce a degraded image, G can be x and y as the degraded image here for us, which will be entered to the restoration filter. And then you can see the degradation process, which will be mathematically expressed as below function of J, X, and Y, H, F, X, and Y, and eta, X, and Y here. Then, if we want to show this G as the matrix, we can have something like G is equal HF plus eta, which F, G, and N are Mn by 1 column matrix, which formed by stacking the row of the M by N matrix formed from the extended, means that zero padded function. Then we can have the F, X, and Y, and GE, X, and Y, and eta, X, and Y of original function of Fxy, Jxy, and eta respectively. H is Mn by Mn as a block circulant matrix, which is formed by stacking the circulant matrix, and H is in the term constructed from J term row of the extended function. And then HE is the original impulse or unit sample or point spreaded function, which we can after that have the term of HXY of degradation term. Then if I want to uniform what I say regarding the term of H, I can have the left side and right side matrices regarding this model, which is show the parameter of H in the form of matrix. That was the model that we can assume for the degradation or restoration process. But after this, we want some algebraic approach for the image restoration. First of all, we should know the objective of image restoration is to estimate somehow the original image. F from the degraded image, and G is using some knowledge or assumption about capital H or small h, which we had in the previous formula. Then the objective of algebraic approach is to seek and estimate the F prime of the original image. Then F from the degraded image, and G such that predefined criterion function is minimized. Based on this, we can have two basic algebraic approach. One is that unconstrained and constrained resortation, and the basic degradation model. Then the new concept of unconstrained image will come. Okay. Into the picture, which in that, as you remember, the basic image degradation model was this plot: fxy, degradation, eta x1, and gxy. Then from that, if you want to calculate the eta from that, we can say that G minus HF in the form of matrix that we have. And in the absence of any knowledge about this noise, this term of eta, the objective of unconstrained resortation is to sync and estimate f prime of the original image. F from this degraded image, and G is such that HF prime approximate G and the norm of the noise term in minimize. Then in the form of formula, if I want to know that F prime is can be founded by the absolute value over by 2 of eta, which is the absolute value of G minus HF prime. And if we want to minimize that, this eta power by 2 can be equal to the eta transpose multiplied by n. And then we can have the below formula regarding that, which can be the norm of G minus HF prime. The minimization of equation 2 that I show can be achieved by differentiating it with respect to the f prime and equating the result to the 0. Then if this differential term will become to the 0 and we solve this differential equation, we can find that f prime is equal to h inverse multiplied by g, which is we can call as the inverse filtering. Then now what we find? We find the mathematical formula for our inverse filtering in the unconstrained resortation method. Okay, as you remember, we talked regarding the frequency domain, which in that, if now the terms that I teach you in the form of the time, now I want to travel in the form of the frequency. Okay, then in that, what should be my h? It can be shown with the what can be my f prime equation in the form of frequency domain. It can be shown with the equation number 5, which in that we can have the f prime of u and v and g of u and v divided by h u and v, where f prime u and v, g u and v, and h u and v are the Fourier transform of the f, g, and h respectively. Why Fourier transform? Because now we travel in the frequency domain from the time domain, and in the present of the noise, if we add the noise to that, then again we can take the Fourier transform from the eta, and then we have the n of uv divided by huv, and it's a term which is added by taking the Fourier transform of the noise eta here. Then there are some disadvantages for this inverse filtering or unconstrained resortation. First is that the complete knowledge about H and eta is required. And second is that this resortation process is very sensitive to the noise. Then we can say that is the resortation result is dominated by the noise if H, U, and V is 0 or small. Then remember that sensitivity to the noise of the method is not that much good. It means that somehow it will make the unstable output, in which it's obvious in any system it can be happened if it's related to the noise. That was unconstrained. But what about constrained resortation? Again, come back and see the degradation and resortation model. And from that and from the basic image model, we can have again the eta of the J minus HF, as we showed the formula here. Then the objective of constraint resortation is to seek an estimate of f prime of the original image. F from the degraded image and G such that the accretion function, we can have the equation number 2. And if again I want to make this and minimize this, I can tell you that again same things which happen with the unconstrained things will happen for the eta, and the absolute value of that will be equal to eta transpose by n. Okay. Now we will see one term of the alpha as the Lagrange multiplier and Q as the operator on the F. Again, if I want to make the minimization of equation 2, I should differentiate it with respect to F prime, and the equation number 3 will come. And then from equation number 3, if I solve it, I can now have another form of F prime, which is in the form of constraint resortation 1, and then the lambda, which is equal to 1 divided by alpha. This yields the different solution for different choice of the Q, and then now I can have the constraint resortation formula and modeling. What I should do, I should have now the least mean square or Wiener filter, which will be obtained by defining the key Q transpose by Q and some correlation matrix of F and correlation matrix of eta, which from equation 4 and 5, I can have the equation number 6, and with the help of equation number 6, we can again travel to the frequency domain representation of equation number 7. Now you can see the result by taking the Fourier transform and see that the new mathematical form will happen inside the domain, inside the frequency domain. In this equation, F prime U and V, H U and V, and G U and V are the Fourier transform of F prime, H, and G, and SH and SF are the power spectral density or PC of H and F. Then if in above formula we will put the eta equal to 1, then the equation 7 become Wiener filter. If with variable eta, then equation 7 becomes so-called parametric Wiener filter. If S eta U and V is equal to 0, means that there is no noise in my system, and then equation 7 become inverse filter. And if H, U, and V is equal to 1 for all U and V, no degradation and only noise we have. Then equation 7 becomes the smoothing or noise removal filter. And then now we need some constraint least square resortation, which with defining the Q is equal to P, where P can be the Laplacian smoothing matrix. Then the equation number 4 for me become F prime H transpose H plus lambda PT P, which all the formula which I had 2 years should be inverse and multiply by H transpose D. Then the frequency domain representation of equation 6 become like equation 7 as we show, which in that PU and V is the Fourier transform of extended version of 2D Laplacian operator of Pxy, which given y in the equation 7. For the part which I teach till now, these we have some work with just this frequency domain, and whatever I will tell you are some proof and some mathematical approach to know that from where these formulas come to picture. Then for the constraint least square resortation, we can assume suppose Px and y as this matrix, which is the norm of the noise, eta can express in the term of mean, and mu, eta, and standard deviation as the formula that we have. Then M and R are the dimension of the noise matrix that we have. Then with the construct least square, we can have the procedure or algorithm that we have. The procedure or algorithm for construct least square resortation is that with the step 1, we will initialize the lambda and estimate the eta using the below formula. And then in step 3, we will compute the F prime UV, and hence F prime is using the Fourier transform act or frequency domain formula, which in that the PU and V is the Fourier transform of extended of 2D Laplacian operator of Pxy. This is the algorithm and process which we may have in constraint least square resortation. And this is actually what will happen when you will put the formula in the MATLAB. Okay. Suppose then if again I have Pxy, I can calculate with the previous formula and reach to this matrix. With the step 4, we can compute the residual R and hence F and G, and using the formula and then increment of eta F B eta, we can have the decrement part and increment part as we show in step 4 and 5. And then with the step 6, again, we will return to the step 3 to do that. Maybe you will find this formula are boring, but these are the parts that we should know what will happen. Rarely we are going to ask what is that formula. It's not exactly our work, it's work of the mathematical part, mathematical concept. We just going to use this formula, and then don't worry about how to using this formula. We have the code which we will act on the figure, and then the output will come. But to analyze the output better, we need to have some background regarding the mathematical part of this formula and this process. Okay, that was the construct least square resortation. After that, we need one new concept, which we call it pseudo inverse filter. As you see in the inverse filtering technique, it's often practically difficult to obtain the exact inverse of 1 divided by h of degradation function, and which h is the stable. Hence, the stable version of exact inverse of degradation function, we know it as the pseudo inverse filter. And in that, we need the linear and position invariant degradation. A degradation system, if we know h as the linear formula of h, as we show here, a degradation system, h is the position invariant if we have the h of fx and y equal to gx and y, and then with that you have the alpha and beta, which will be decrement from the x and y. Then in the j also you have the decrement from these two terms. The degradation system H is LPI or linear position invariant if it's linear and position is invariant. This is another term that we will have. Then what we learned through all this thing, we just review some mathematical part or mathematical formula regarding the resortation concept, and then we find regarding the pseudo inverse filter and inverse filter. These are some topics which is highlighted for today. The other part is geometric transformation, which in that they call it rubber sheet transformation, because they may be viewed as the process of printing an image on a sheet of rubber and then scratching this sheet according to some predefined set of the rules. A geometric transformation consists of two basic operations. First is that a spatial transformation, which defines the rearrangement of pixels on the image plane, and another one is the gray level gray level interpolation, which deals with the assignment of the gray level to pixel in the spatially transformed image. Again, if we want to go deeply inside the formula which make our geometric transformation, we can say that in this the spatial transformation, an image with the pixel coordination of x and y can be undergoes some geometric distortion, which will be produce an image of G with the coordination of x prime and y prime. Then this transformation may be expressed as x1 and y1, which again we have the R and S as the spatial transform that produce the geometrical distorted image. We can have some example of R, x, and y equal to x divided by 2 and s as y divided by 2. This transformation is shrinking the image. You will see that any point in these two will be divided by 2. Then if any pixel divided by 2, obviously the total image will shrink. If in the formula Rx and y and Sx and y can be expressed analytically, then the original image that we have, the original image of f x and y can be easily recovered from the disordered image. And gx prime y prime, by applying the transformation in the reverse direction, we can have it. But if Rx and y and Sx and y cannot be expressed analytically, as is the case in the most practical application, the spatial relocation of pixels are formulated using the typons, which are the subset of pixels whose location in the distorted and corrected image is known precisely as shown in the next picture that I will show you. A set of equations are derived from the spatial relocation of this typon, and the reverse transformation is achieved by using them. Here you will see the typons of my image, and you will see the geometric transformation, which will be happened by if the term of R and S cannot be analytically analyzed and do it. Here, after this transformation, we have another concept which we call it Gray-Level Interpolation. In this Gray-Level Interpolation, when performing the reverse geometrical transformation to obtain the original image of f, x, and y from the distorted image of g, x prime, y prime, depending on the coefficient of the equation for r, x, and y and s, x, and y, the coordination of x prime, y prime may be integer or non-integers. And for the digital image, the coordination must be exactly integer. Hence, for the non-integer coordination, the integer equation may not have any gray level values, and obtaining the gray level value for such coordinates is known as the gray level interpolation. This is the concept which we know regarding the interpolation. The gray level interpolation techniques include the cubic convolution interpolation and bilinear interpolation, which we are going to talk regarding them. First is that zero order interpolation, which is the base and nearest neighbors approach. And you will see the mapping of integer x and y coordinates into the fractional coordinate of x prime and y prime. The selecting of closest integer coordinate neighbor to x prime and y prime, and the assignment of gray level of this nearest neighbor to the pixel which is located to x and y is the job for the gray level interpolation method. You will see in the figure also, if you assume the f prime x and y and g x prime y prime, if I want to go from the gray level assignment or spatial transform, you will see here that from x to x prime is the spatial transform, which there we have the gray level interpolation based on the nearest neighbor. And then by the nearest neighbor that you will see, we can have the gray level assignment and come back to my x and y coordination or dimension in my image. In the gray level interpolation, we have some terms, as I tell you. One is that cubic convolution interpolation, and another one is bilinear interpolation, which in them, cubic convolution interpolation, this fits a surface of sin z divided by z type through the much larger number of neighbors. say suppose 16, in order to obtain the smooth speed estimate of gray level at any desired point. And bilinear interpolation is this use the gray level of four nearest neighbors, usually in the adequate. The gray level value of non-integral pairs of coordinates will donate a v of x prime y prime and can be interpolated from the values of the neighbor by using the relation of v x prime y prime. As the formula that I showed, we have four coefficients which are easily determined, the four equations in four unknowns that can be written by using four unknowns neighbor of f x prime y prime. And when these coefficients have been determined, v of x prime y prime is compute, and this value is assigned to the location of f, x, and y that yield the spatial mapping into the location of x prime y prime. Here is the image showing the tie points in the A1, means that A, figure A, and B will show the tie points after geometric distortion. Number C is the geometrically distort image. Number D is the resorted result, as you will see. And again, C is the image distorting by the distorted E. Sorry, E is the distorted using the bilinear recursion, and F is the resorted image. Okay. Maybe now you may have some confusion regarding the act of them. We will review all this filter with the help of MATLAB uh, in next lectures. But just now I wanted to give you some mathematical um, idea regarding how this interpolation will come to picture. Now, please have this idea. With the next part of today's lecture, we will talk more regarding the interpolation part. Then it may become more clear for you to understand. That was the some mathematical part which is mentioned in your book, and we should review it. But maybe somehow you feel that you need more description regarding that. Then, especially for the interpolation part, I try to find more source and more descripting things which help you to understand this concept better. Uh, this is not from really from the some academic reference like the book, but this part that I will teach you, and purposefully I make it separate from the means that the first lecture that we have is that these are from some blogs and some white paper, which will help you to understand the topic better. Okay. Then from one side, we can say that maybe it's not acceptable in um, university learning process. But from other side, we can say that because it's written in the other words, which more elaborate and also have more description regarding the topic that we want, it's very useful. That is why I put it as a separate PPT for you. And I call it interpolation more concept or more deeply regarding the interpolation. Now here you will see more reaction and effect of the interpolation part, and then it will help you to understand it better. Also, please remember that um, from last week we start like this. First, we will say the theoretical, try to give more description regarding that. Then for the next lecture, again, one by one, we will start to do the action and see the coding of the each part. Means that, as you see, I personally test each code and with the one fixed image, and you also should uh, test it with first image that you use in your task Then at the end of the lecture series, you will have the set of nice effect and nice coding with your photo, which you choose. Also, I should remind some students that they didn't send the task number 4. It's not good. Please make this task or serious. It will help you to understand the topic better. This topic, if I want to talk just mathematical part, whole term, whole semester, I can speak just regarding the mathematical part. And if I want to just talk regarding the MATLAB part, one and more than one semester, I can just talk regarding the mathematical part. Then that is why we should shift between MATLAB and theoretical and MATLAB to have the better understanding. Okay, just Roy, if everything is okay, I will start. Just give me the feedback from the sound and PPT. Okay. Why we don't have feedback from class? Kaya, can you hear my voice or no?
Yes, sir. I can see the PPT.
Okay.
Everything's fine.
Okay. Then if you have the feedback, please give me. Otherwise, I thought that all of you are asleep. Okay. Reza, is it okay with you also? Let me check with some students.
Okay, sir. Everything is okay.
Okay. Let us see. Then this part I call it interpolation, more concept, or deeply we will talk. First of all, have the clear concept regarding the resizing the image. When you will resizing the image or zooming, you will create the new pixel location and assigning the gray level value to those locations. Okay. Maybe you have done this before. When you zoom an image, the quality and clarity of the image come down. How we will do this zooming? This is by the interpolation job. The solution for doing the zooming is interpolation job. Let us see. Image interpolation will occur when you resize or distort your image from one pixel grid to another one. This resizing is somehow necessary when you need to increase or decrease the total number of pixels, whereas remapping can occur when you correcting for lens distortion or rotating an image. Then we can say that zooming refers to increase the quality of pixels so that when you zoom an image, you will see more detail. But maybe with this job, you will also have more detail, but the clarity also somehow will be changed because now you have the changing the coordination of your image. Suppose if I'm in X, Y, and Z, if I multiply it, means that zoom it by X2, each point will be multiplied by 2 and it's become zoom like that. Okay, clear? Then interpolation work by knowing the data to estimate value at unknown point. Image interpolation work in two directions and tries to achieve the best approximation of pixel intensity based on the value of surrounding people. Common interpolation algorithm can be grouped into adaptive and non-adaptive one. Adaptive method change depending on what they are interpolating, whereas non-adaptive method treat all pixels equally. Non-adaptive algorithms are including nearest neighbor, bilinear, bicubic, SPLINE, SINC, ZANGZO, and others. Langzone and others. And adaptive algorithm are many probability algorithm in licensed software such as PhotoZoom, Genius, and that they will use that adaptive part. Many compact digital camera can perform optical and digital zoom, and camera perform the optical zoom by moving the zoom lens so that it can increase the magnification of the light. However, a digital zoom degrades the quality by simply interpolating the image. Even though the photo with digital image contain the same number of pixels, the details is clearly far less than with optical zoom. Zooming and shrinking will be introduced for this purpose interpolation and discussed here. And many various interpolation techniques will be introduced of three of them, namely nearest neighborhoods, bilinear, and cubic interpolation. Now I will give you one small sample that maybe the previous formula that we taught become more clear. You will see the 2D interpolation here and see the first photo, and after the interpolation, what it happened. For the nearest interpolation, as we talked, it will find the near neighbor pixel of MEMA and then do the interpolation of that. With the bilinear one, you will see that little feature is blue. And bicubic one, also, you can see the result as we shown in the figure. Image interpolation we have in all digital photos at some stage, whether this will be biodemonstrating or in the photo enlargement. It happens anytime you resize or remap. We can say remap is distort your image from one pixel grid to another one. And image resizing is necessary when you need to increase or decrease the total number of pixels, whereas remapping can occur under the wider variety of the scenario, something like correcting for lens distortion, changing the perspective, and rotating an image. If I want to say the interpolation act, this photo is very nice. Suppose the word of interpolation, if I resize it, you will see that the size of the word is changed. But if I want to say distort, you will see the effect of interpolation like this. Even if same image resize or remap is performed, the result can vary significantly depend on the interpolation algorithm. It's only an approximation, therefore an image will always lose some quality each time interpolation is performed. Then now you may again recall, for zooming and creating the new pixel, interpolation is the method that we can do. But now let us see some act of interpolation on some image. Suppose image interpolation will work in two directions, as we say, and try to achieve the best approximation of picture's color and intensity based on the value surrounding the pixels. You will see some illustration of how resizing and enlargement is work. See, suppose if I enlarge 183% for my original image, the before interpolation, we have some dot. But after that, you will see that some gray pixel are added. What is that? You will see I have some question mark here, which after the interpolation in any method, okay, some gray level between them, some neighbors, which has the specification of up and down or right, left, up, down information of the pixel location. It has some gray value like that. Now you can compare after interpolation and before interpolation of an image here in this photo. Common interpolation algorithm, as we say, we have in the form of adaptive and non-adaptive one. And we talked that adaptive method change depend on what they are interpolating. Some of them will sharp the edge and some of them will smooth the texture. Whereas non-adaptive method treats all pixels equally. Okay? Then remember these 2 points. In non-adaptive one, which we can include some method like nearest neighbors, bilinear, bicubic, spline, and other, which are depending on their complexity. These use anywhere from 0 to 256 or more adjacent pixels with interpolating. The more adjacent pixels they include, the more accurate that they can become. But this comes at the expense of much longer process time. This algorithm can be used to both distort and resize image. Then, if I have to distort or resize the photo, non-adaptive algorithm will be the good interpolation approach. But what about adaptive algorithm? In the adaptive algorithm, which includes many properties algorithm in licensed software, like photo zoom and some others which are found. Many of them will apply a different version of their algorithm on pixel by pixel basis. And when they detect the presence of an edge, aiming to minimize the unsightly interpolation artifacts in region when they are most apparent. These algorithms are primarily designed to maximize the artifact-free detail in large photos, so some cannot be used to distort or rotate an image. Then, if we want to review, the nearest neighbor interpolation is the most basic and requires the least processing time of all the interpolation algorithm because it only considers one pixel, the closest one to the interpolated point. And this has the effect of simply making each pixel bigger. Bilinear interpolation will consider the closest 2 by 2 neighbor of known pixel value surrounding. It then takes the weighted average of these 4 pixels, up, down, right, and left, to arrive at its final interpolation value. And this result is much a smoother looking image than their nearest neighbors. And the bicubic interpolation goes one step beyond the bilinear by considering closest 4 by 4 neighbors of known pixel for total of 16 pixels. Means that in bicubic you have 16 pixels. Okay, and since these are at some various distance from the unknown pixel, closer pixels are given the higher weightage in the calculation. Bicubic produce the notably sharper image than the previous 2 methods, and it's perhaps the ideal combination of processing time and output quality. For this reason, it's a standard in many image, something like Adobe Photoshop. They try to use the bicubic interpolation. We have some more interpolation method, which we know them as the we know them as the, just 1 minute, I think. Yes, higher order interpolation, something like SPLINE and SINC, which they are many, including many other way of interpolation, and are thus also much more computationally intensive. These algorithms include the SPLINE and SINC and return the most image information after interpolation. They are therefore extremely useful when the image requires the multiple rotations, distortion in the sphere steps. However, for some single step enlargement or rotation, these higher order algorithms provide the dimensioning visual improvement as process time is increased. And now we will see the interpolation artifacts to watch out for. Suppose all non-adaptive interpolation attempt to find an optimal balance between three undesirable artifacts. First one is edge hole and blurring and aliasing, as you will see the result here in the aliasing with the 40% of interpolation. Blurring and edge halo, which are the three, we can say, problem that we have in artificial artifacts of interpolation. Even the most advanced and non-adaptive interpolation always have to increase and decrease one of above artifacts at the expense of their two. Therefore, at least one will be happened. One of these three problems we may have, which we should work with that. Now I bring one example for the adaptive interpolation, which may or may not be produced some artifacts. However, they can also induce non-image texture or a strange pixel at a small pixel. You will see that if I do the 220% enlargement for mine, I see that after adaptive interpolation, what will happen to my photo. But on the other hand, some of these artifacts from adaptive interpolation may also be seen as benefits, since the eye expect to see the details down to the scale, small scales in fine texture area, and these patterns have been argued to trick the eye for the distance. Some of these artifacts will can help you to see the deep inside the image. As we say, one of the problem was aliasing, which anti-aliasing is the process with attempt to minimize the appearance of the alias or jagged diagonal edge, term jaggings, and this gives the text or image through the digital appearance. See here some alias and anti-alias job I have done with the enlargement of the 300% interpolation. Then you will see some shade on the anti-alias one and alias one after it happened. Okay, then anti-aliasing will remove these jaggings and give the appearance of the smoother edge and higher resolution, and it's worked by taking into account how much an ideal edge overlap adjacent pixel and the alias and the alias edge simply round up or down no intermediate value. See here the perfect diagonal and re-sampled for the raw resolution, which are shown in the below figure or below image, as you will see. A major obstacle when we enlarging an image is preventing the interpolated from including or excavating aliasing. Many adaptive interpolators detect the presence of edge and adjust to minimize the aliasing while still returning the edge sharpness. Since an anti-aliased edge contains the information about the edge location at higher resolution, it's also have the powerful adaptive interpolation and could at least uh, partially constructed this edge when enlarging. Maybe it's good for us to know that many compact digital camera can perform both optical and digital zoom, and camera perform an optical zoom by moving the zoom lens so that it's increase the magnification of light before it's even reach the digital sensor. In construct a digital image as a sample which I bring here with the optical zoom and digital zoom, you'll see that digital zoom degrades the quality by simply interpolating the image after it has acquired the sensors. Now you will see that when I do the zooming job with optical of 10%, 10 multiplied by 10, with digital and optical one, what will happen with my image and what should be the quality that I can have as the output point. Even the photo with the digital image contains the same number of pixels. The details are clearly far less than optical image, and digital zoom should be almost entirely avoided when you will take the photo. And remember that uh, in any case, then you use the digital zoom to frequently, you should take some other lenses to do it better. Why I tell this interpolation job and also ended with the zooming job? Because somehow you know that analyzing the image and having the good image need to have the having the good analyzing for the image need to have the good image. Then remember that when you take any image, try to don't put much more zoom on your image and have it as something like natural form, because this zooming will corrupt your source of information or source of image, which may not will be successful when you analyze that image. Okay, this part which I give you now was regarding the interpolation technique and part. We will test uh, all this in the next lecture with the help of MATLABs and some previous part which is remain. Means be ready for the nice MATLAB part. Still, I go very slowly inside of MATLAB because I feel that some of you have problem with the MATLAB part, but it will remove, don't worry. And please, if you have problem with working with MATLAB, just inform me that we can solve the problem. It's okay for today for the topic.